All right, let's dive right into one of the biggest, most mind-bending mysteries in all of physics. Think of this as a cosmic detective story, a crime that seems to violate the fundamental laws of the universe. We're here to solve the case of the lost information. So let me ask you a question. If you take a book and burn it to a crisp, is that story gone forever? You'd probably think so, right? But believe it or not, physics tells us something totally different. The answer is no, it's not gone. In theory, if you could capture every single particle of smoke, every tiny speck of ash, every bit of heat that was released, you could piece it all back together and reconstruct the entire story. See, the information isn't actually destroyed, it's just scrambled. And that's a core rule of our universe. Information can never truly be lost.
But there's one place in the cosmos that seems to be the ultimate exception to this rule. A place that acts like a cosmic crime scene, where this fundamental law just gets thrown out the window. And yeah, you guessed it, I'm talking about black holes.
You see, according to Einstein's general relativity, a black hole is almost absurdly simple. It doesn't matter what you toss into it, a star, a planet, an entire library's worth of books. The black hole only remembers three things about it: its mass, its charge, and its spin. That's it. All that rich, complex information about what the book was, it seems to be completely erased from existence. Physicists have a great name for this. They call it the no-hair theorem, because a black hole has no other complex features.
And this, right here, sets up an absolutely colossal battle. It's a clash between the two great pillars of modern physics. We're talking about a genuine paradox, where our two best theories for describing reality give us completely opposite answers.
So here's the standoff. On one side, you have general relativity, which says, yep, a black hole is the universe's ultimate information shredder. What goes in, stays in, and gets destroyed. But on the other side, you have quantum mechanics, which insists, no way, information can never, ever be destroyed. It's a principle called unitarity. Clearly, one of these has to be wrong, or there's a huge piece of the puzzle that we've been missing. This is the heart of the black hole information paradox.
Then, back in the 1970s, the one and only Stephen Hawking dropped a massive clue into the middle of this mystery. He realized that because of quantum mechanics, black holes aren't perfectly black. They actually leak a tiny bit of energy over time, something we now call Hawking radiation. And over trillions upon trillions of years, they can completely evaporate and disappear. And at first, everyone thought, aha, that's it. Maybe the information just leaks back out with this radiation. Problem solved, right?
Well, not so fast. Here's the twist that made the paradox even worse. Hawking's own math showed that this radiation is thermal. That means it's completely random. It's like turning on a radio and only getting white noise, pure static. There's no song, no secret message, just random noise. So the black hole evaporates, the radiation comes out, and the information from our book is still gone. The escape route was actually a dead end.
So for decades, physicists have been stuck, but this is where our story takes a really sharp turn. Because a new idea asks a radical question. What if the information isn't inside the black hole, and it isn't in the random radiation? What if we've been looking in completely the wrong place? What if we've misunderstood the very nature of space-time itself?
Now get ready for this, because this is the mind-bending idea. What if space-time isn't just a boring, passive stage where everything happens? What if space-time itself is an active participant, a kind of cosmic hard drive that can actually remember what happens on it?
This brings us to our prime suspect in this case, the quantum memory matrix, or QMM for short. This idea proposes that if you could zoom in on space-time way down to the tiniest possible level, the Planck scale, you'd find it's not smooth. It's actually pixelated, made up of these tiny fundamental units, or quantum cells. And here's the kicker. Each one of those cells can act like a tiny bit of memory, storing information.
So, how would this work? Well, when our book falls into the black hole, it doesn't just vanish without a trace. The theory says that as it passes the event horizon, it leaves behind a perfect quantum imprint of all its information, right there in those cells of spacetime. The best analogy is to think of memory foam. You press your hand into it, you take it away, but the imprint, the information about the shape of your hand, is still there. Spacetime literally remembers the story.
Okay, so I know what you're thinking. That's a cool idea, but if the information is just stamped onto spacetime, how does it ever get out? I mean, how do you read what's written on this cosmic memory foam?
This is where it all comes together in a beautiful three-step process. First, stuff falls in and its information gets encoded onto the space-time grid. Step 2, that information is safely stored in the quantum memory matrix for as long as the black hole exists. And now for step 3, the genius part, retrieve. As that Hawking radiation slowly leaks out, it's not just escaping into empty space, it interacts with these imprints, and in doing so, it picks up the information that's stored there. So the radiation is no longer random static. It's the messenger carrying the story of our lost book back out into the universe.
Now, this is an incredible story, right? It sounds almost like science fiction, but is it actual science? And the thrilling answer is yes, absolutely. This isn't just a neat idea. It makes real, concrete predictions that we can actually go out and test.
The most direct way to prove this would be to find that message in the static. The quantum memory matrix predicts that Hawking radiation won't be perfectly random. Because it's carrying information, there should be tiny, subtle patterns, little modulations in its energy that just wouldn't be there if it were pure noise. Finding those patterns would be the smoking gun. It would be like finding the QMM's fingerprints all over the crime scene.
And that's not all. There are other places we could look for these cosmic echoes. For example, these space-time imprints could create tiny, faint blips in the gravitational waves we detect when black holes merge. Or they might have left a very specific signature on the cosmic microwave background. You know, the afterglow of the Big Bang itself. We could even hunt for unique signals coming from tiny, ancient black holes that might be evaporating right now. We have multiple leads to follow.
So why does all of this matter so much? I mean, why are we so obsessed with this case of the lost information? Because it was never just about black holes. The paradox is a flashing red light warning us that our two best theories of the universe, general relativity and quantum mechanics, don't play nicely together. A solution like the quantum memory matrix, which perfectly bridges that gap, wouldn't just solve the paradox, it would be a giant leap toward a unified theory of everything, the single biggest goal in all of physics.
And this leaves us with a truly profound final thought. This idea completely changes how we think about the universe. It suggests that the fabric of reality, space-time itself, isn't just the empty stage for the story of the cosmos. It is the story. It's the paper on which everything is written, a cosmic memory matrix that holds the imprint of every single thing that has ever happened.
Welcome to The Explainer, where we break down big ideas. And today, we've got a question that sounds like it's straight out of science fiction, but it's actually, well, it's one of the biggest puzzles in modern physics. Could a black hole be the universe's ultimate hard drive? Yeah, you heard that right. We're diving into a cosmic mystery that has had scientists scratching their heads for decades.
So yeah, we are absolutely tackling one of the most mind-bending puzzles in all of physics, the black hole information paradox. And really, it all just boils down to this one single, crucial question.
The best way to think about it? It's like a cosmic crime scene. You've got a fundamental law of physics, this core idea that information can never be destroyed. And it looks like it's being broken. And look, this isn't some minor rule bending. This is a full-on heavyweight title fight for the nature of reality itself, and it pits our two most successful theories of the universe directly against each other.
All right, so in one corner, you've got quantum mechanics. That's the rule book for everything that's super, super small. And it has this one non-negotiable law, a principle called unitarity. All it says is information can never, ever be permanently destroyed, period. But then, in the other corner, you have general relativity, right? Einstein's masterpiece on gravity, and it describes black holes as, well, cosmic shredders. General relativity says that once anything crosses that event horizon, the point of no return, all the information it carried is just gone, erased forever.
And just when you think it couldn't get more complicated, Stephen Hawking comes along and throws this massive curveball into the mix. See, he figured out that black holes aren't entirely black. They actually leak a tiny bit of radiation over time, and because of that, they can eventually just evaporate completely. Gone. But here's the real kicker. This Hawking radiation, as we call it, seems to be totally random, completely thermal. It carries absolutely no information about what fell into the black hole in the first place. So, when the black hole is gone, where did the information go? It's a huge problem, because according to physics, that's just not supposed to happen.
Okay, and this is where things get really, really interesting. A new theory suggests that the clue to solving this whole mess isn't some exotic new particle we have to find. Nope, it might be hidden in plain sight in the very fabric of the universe itself.
So, there's this new hypothesis coming out of a 2024 paper by Florian Neukart and his team, and it offers a really compelling potential solution. It's called the Quantum Memory Matrix, or QMM for short, and let me tell you, it proposes a truly radical idea about what space and time actually are.
Basically, the QMM hypothesis asks us to completely rethink how we see spacetime. Stop thinking of it as just this passive, empty stage where all the cosmic drama plays out. Instead, what if spacetime is an active participant? What if it's a gigantic cosmic hard drive?
Okay, so this whole idea is built on two core principles. Let's break them down. First, you know how a digital picture is made of pixels? Well, the QMM theory says spacetime is kind of the same. It's quantized. Down at the impossibly tiny Planck scale, it's made of these fundamental, indivisible units. You can literally think of them as the pixels of reality. All right, and the second principle is this. When some quantum event happens, a particle zips by, whatever, it doesn't just pass through these spacetime pixels without a trace. No, it actually interacts with them, and it leaves behind something called a quantum imprint. You can think of it like a tiny scar or a little modification to that specific unit of spacetime, a scar that encodes the information of that event. Okay, hold on. Spacetime is a hard drive. It records everything. That's a huge idea. But how in the world does that help us get information back out of a black hole? Well, that is the incredible revelation at the very heart of this whole QMM idea.
So the framework lays out this really simple but honestly super elegant three-step journey for information. It's encoding, storage, and finally retrieval.
So, first up, encoding. Imagine some matter falling towards a black hole. As it gets close, its quantum information doesn't just disappear when it hits the event horizon. Nope. Instead, it gets imprinted. You could say written, directly onto those space-time pixels right there at the edge of the black hole.
Next, step 2, storage. And this is key. That information isn't actually inside the black hole, down in the singularity. It's being held securely in the very structure of spacetime around the black hole. The cosmic hard drive is just holding on to the file for safekeeping.
And finally, we get to the most crucial step of all, retrieval. Remember that Hawking radiation we talked about, the stuff leaking out? Well, the QMM theory says it's not random at all. As those particles pop into existence right at the edge, they interact with that imprinted spacetime. They essentially read the data that's been stored there, and then they carry it away, piece by piece, as the black hole slowly evaporates. I mean, this just completely flips our view of Hawking radiation on its head. It's no longer just meaningless random thermal static. If the QMM hypothesis is right, it becomes an information-rich signal. It's literally broadcasting the contents of the black hole back out into the universe. See? The information is never lost. It's just stored for a while and then re-released.
Okay, so this is a really beautiful, elegant idea. But is it science? And the answer is a resounding yes, absolutely. You see, unlike a lot of other proposed solutions to this paradox, the QMM hypothesis isn't just a clever story. It actually makes specific, testable predictions. It's basically daring us to go out and find these scars on spacetime.
So, how would we actually find them? Well, scientists are on the lookout for two main signatures. First, when two black holes merge, they send out those gravitational waves, right? Ripples in spacetime. Well, those waves might carry subtle glitches, tiny little anomalies caused by these imprints. And second, we can look for features in that faint glow of Hawking radiation that prove it's not purely thermal, not purely random.
Now check this out. The core difference really comes down to this. The standard prediction for Hawking radiation says it carries very little specific information. That's the bar you see on the left. But the QMM prediction over on the right says that radiation should be incredibly information-rich. So if we could ever detect that higher level of information, that non-random, non-thermal signature, that would be the smoking gun. That would be the proof. When you put it all together, the quantum memory matrix offers just a stunningly elegant solution. It manages to save that sacred law of physics, that information can't be destroyed, and it does it not by breaking anything, but by completely reimagining the very stage on which all of physics plays out.
So in this picture of the universe, information is never really lost in a black hole, because in a way, it was never truly in it to begin with. It was just written into the very source code of the universe itself.
And that, of course, leaves us with one final, really provocative thought to chew on. If space-time really is a universal memory matrix, and it's recording every single interaction that has ever happened, what kind of story do you think is written in the empty space all around you right now?
So, what really happens when you throw something into a black hole? I mean, does it just disappear forever? You know, for decades, that really simple question has created this massive, massive paradox right at the heart of physics. But what if a new theory is right? What if the answer is hiding in plain sight, and the universe itself has a memory? Today, we're diving deep into the quantum memory matrix.
We're going to treat this like a cosmic detective story. First, we'll lay out the crime scene, the paradox itself. Then we'll introduce our main suspect, this idea of a hidden memory in space-time. We'll look at the method, how information actually gets saved. We'll compare it to some other theories. And then finally, we'll go searching for the evidence that could crack this whole case wide open.
All right, let's get right to the scene of the crime. We are headed to one of the most extreme places in the entire universe, the event horizon of a black hole. Because this is where two of our most fundamental theories about how reality works, general relativity and quantum mechanics, they don't just disagree, they basically go to war with each other. This is the question, isn't it? The one that's kept physicists up at night for years. Think about it like this. If you burn a book, all the information inside isn't truly gone. It's just been scrambled, into ash and smoke and heat. And in theory, you could piece all of that back together. But a black hole? That's a whole different story. And for decades, nobody had a good answer.
And here is the absolute heart of the problem. On one hand, you've got Einstein's theory of general relativity. It tells us that once anything crosses that event horizon, it is gone, for good. Its information is completely erased from our universe. But on the other hand, you have quantum mechanics, which has this one single ironclad rule. Information can never be destroyed. It just can't. So one of these pillars of physics has to be wrong, and that is a major crisis. And then Stephen Hawking made the mystery even deeper. He figured out that black holes aren't actually truly black. They leak this very faint glow. We call it Hawking radiation now. And over incredible amounts of time, they evaporate completely. Now, here's the problem. This radiation seems totally random. It's like meaningless static. It carries zero information about what fell in. So once the black hole is gone, the information is gone too. And that violates a core quantum principle called unitarity, which is really just a fancy way of saying information has to be conserved, always. So let's bring in our main suspect in this cosmic investigation. What if the solution isn't buried in some exotic new dimension or some weird undiscovered phenomenon? But what if it's been here all along, woven into the very fabric of reality itself? This is where a pretty radical new hypothesis comes into play. So, meet the quantum memory matrix, or QMM for short. This theory completely turns our idea of space-time on its head. See, we usually think of space-time as just a passive stage, right? A backdrop where all the events of the universe play out. The QMM hypothesis says, no, that's wrong. It suggests that space-time is actually an active participant. It can literally remember what happens within it. Probably the easiest way to wrap your head around this is with a pretty simple analogy. Just imagine that space-time is a massive cosmic hard drive. Every single interaction, every particle, every event that happens, it doesn't just happen in space-time. It actually writes a tiny piece of data onto space-time itself. Now, this cosmic memory, it operates at a scale that is, it's almost impossible to comprehend. It's called the Planck length. To give you some perspective, if you were to blow up a single atom to the size of the entire known universe, the Planck length would be about the height of one tree on that planet. At this unbelievably tiny resolution, the smooth fabric of space we see, it breaks down. It becomes more like pixels. According to the QMM theory, if you could somehow zoom all the way into this Planck scale, you wouldn't see a smooth, continuous surface. You'd see something more like a grid made up of what are called quantum cells. And here's the core idea. Every single one of these fundamental pixels of reality can act like a tiny bit of memory. It can store information. Okay, so if space-time really is a hard drive, how does it actually record anything? And how does it play it back? Well, the mechanism is fascinating, and it's called a quantum imprint. A quantum imprint is basically like a tiny scar, a permanent modification left on one of those little quantum cells of space-time. When a particle interacts at a specific point, it leaves a trace of its properties, its energy, its spin, its momentum, encoded directly into that location in the grid.
So, here is exactly how this could crack the case. It's a three-step process. Step 1 is encode. As matter falls toward a black hole, it imprints its information onto the space-time cells right there at the edge. Step 2 is store. That information is now held securely in the fabric of space itself, not actually inside the black hole. And then step 3, retrieve. As the black hole slowly evaporates, the outgoing Hawking radiation particles bump into these imprints, picking up the stored information and carrying it back out into the universe. And just like that, the paradox is solved. The information was never truly lost.
Now, this idea of a local memory, that the information stays right where the event happened, is what makes CRICM so powerful compared to some of the other, frankly, much stranger solutions that have been proposed over the years. So let's compare the suspects. You've got the holographic principle, for instance, which suggests information is somehow stored on a distant boundary of the universe. Then there's the firewall theory, which proposes a deadly wall of fire right at the event horizon, but that would totally violate Einstein's predictions. In contrast, QMM keeps the solution simple and, more importantly, local. The information is stored right where it needs to be, without any weird long-distance effects. And this local approach, while it has some huge advantages, it doesn't need any extra dimensions or that famous spooky action at a distance. It keeps the event horizon perfectly smooth, just like Einstein said it should be, so an astronaut falling in wouldn't feel a thing. And most importantly, it gives us a clear, direct way for the information to get back out. It's just an elegant solution. Of course, a cool story is just a story, unless you can prove it, right? I mean, a good theory has to be testable. So how in the world could we ever find evidence that space-time actually has a memory? Well, the amazing thing is, the QMM hypothesis makes real, concrete predictions. If it's correct, we should be able to see its fingerprints on the cosmos. We could look for tiny distortions in Hawking radiation, or maybe find echoes in the gravitational waves from merging black holes, or even spot weird anomalies in the faint afterglow of the Big Bang itself. So take Hawking radiation, for example. If QMM is right, it wouldn't be perfectly random thermal noise anymore. It would be a structured broadcast. It would have these subtle patterns and correlations baked into it, the very information it picked out from those quantum imprints. Detecting that would be the smoking gun. And another place we could look for clues is in gravitational waves. You know, when two black holes merge, the very final ring down of the signal as they settle into one, well, it could contain these tiny echoes, little anomalies in the wave caused by all the information that's imprinted on the space-time right around them. So when you step back, the quantum memory matrix hypothesis is so much bigger than just solving one paradox. It suggests something really profound, that the universe itself might be this vast quantum hard drive, constantly recording its own story in the very fabric of reality, just waiting for us to figure out how to read it.